We're going to keep talking about orbitals, and we're going to talk about orbital diagrams and electron configurations. It's important that you practice these because you'll definitely have to write some of these. So this is, remember, an orbital diagram. The last one you saw was had boxes. Sometimes there's boxes and sometimes they're just lines. And remember that energy is on an increasing scale where the lowest energy 1s orbital is at the bottom, and I'm adding some orbitals here that will be added as we go. Now, there are some crossovers in energy, because the 3D subshell is actually a little bit higher in energy than the 4s subshell, and then it kind of squeezes in before the 4p. And then there's the 5s subshell, and then the 4d subshell is actually higher in energy than the 5s. And we'll talk about how you're going to look at the periodic table and know that. But there are several crossovers. The 4f is another crossover in energy. So the 4f subshell is actually higher in energy even than the 6s subshell. So the numbers don't really necessarily match, right? You can have a subshell in the 4th shell that's higher in energy than the subshell in the 6th shell. But we're going to talk about how you know that from the periodic table. Now, as electrons fill in atoms, there's a principle called the Aufbau principle, and this describes how electrons fill the orbitals. They always fill from the lowest energy to the highest energy. And so if we think about the orbital diagram for hydrogen, hydrogen has a lot of orbitals available to it, but its electron's going to sit in the 1s orbital because that's the lowest energy spot available. It has an electron configuration where we write the orbital designation 1s, and then the superscript 1 designates that there is one electron in that orbital. So 1s is the orbital type, and then that orbital contains one electron. And you're going to account for every electron in an atom using this electron configuration. We're going to keep going, and we're going to talk about the next rule. Is the Pauli exclusion principle. The Pauli exclusion principle states that each orbital will hold a maximum of 2 electrons and that they have opposite spin. So what that means is that when we do the orbital diagram for helium, helium is the second element on the table. It might help for you to have the periodic table out so you can see how we're doing this, but helium houses 2 electrons in its ground state neutral atom, and that second electron is going to go with the same electron, the electron that's already there in the 1s orbital, and it also has opposite spin, so you draw the arrow upside down. The electron configuration for helium is 1s with a superscript 2, 1s2. Now if we keep going, we're going to keep filling in. So we're going to move on and talk about lithium. Lithium is the next element on the table. It has 3 electrons. So those 2 are already there, but the third electron is going to go in the next lowest energy spot, which is the 2s. Its electron configuration is 1s2, 2s1. If we keep going, beryllium has 1 extra electron, so it's going to be paired with the other 2s electron that we already had in there. 1s2, 2s2 is its electron configuration. Can't do that. There we go. 1s2, 2s2, 2p1. Now, if we move on, we've got carbon next. But carbon, we have a new rule that we have to learn. And so the question is, does the new electron go here in the second orbital, or does it go here, or does it pair with the first one? Does it get a roommate? So the third rule is Hund's rule, which says that when multiple degenerate orbitals are available, 1 electron will go in each orbital until all are half full. These electrons will all have parallel spins. So let's talk about that sentence. Multiple degenerate. Degenerate actually means equal in energy. So what you can see there for the 2p subshell is that there are 3 lines. There are 3 orbitals available. They are all 3 equal in energy. And so the next electron is going to go in the second orbital. So basically electrons are like people. They'd rather live alone than have to live with a roommate, because it's just a lower energy situation. And that second electron has the same spin as the first electron, and so they have to both be pointing up in the up direction, or both in the down direction. We usually draw them both in the up direction. Now this is just a lower energy situation, is why that happens. The electron configuration is 1s2, 2s2, 2p2. The different p orbitals are not designated in the electron configuration. We just lump all the p electrons together, so 2p2. Now go on and we talk about nitrogen, it's going to sit in the third orbital. Now something unique about nitrogen is that it has a half-filled subshell, which is more stable than if it were only partially filled. So he's happier like this than carbon was. The electron configuration is 1s2, 2s2, 2p3. And we're going to talk about oxygen. Oxygen has to pair up with one of the other electrons. 1s2, 2s2, 2p4. We're going to keep going. The next one is fluorine, and he has an extra electron here. So if you count the electrons there, 2, 4, 6, 8, 9 electrons, which matches fluorine. And then if you look at the electron configuration, if you add up 1s2, 2s2, 2p5, if you add up the superscripts, 2 plus 2 plus 5, you should also get 9, which is the atomic number of fluorine. And it should be the same as the number of electrons in a neutral atom, right? Now we have neon. Neon is a noble gas. We're going to add our last electron to this 2p subshell. So half-filled subshells are stable. We already said that with nitrogen. Filled subshells, like we have here, this 2p subshell, is even more stable. So he's happy, but he's also got his party hat on, so he's super happy. Now, this is actually even more stable because this is an entire filled shell. So this is a filled second shell, and this is the most stable situation you can have. So he's got his party hat on, but he's also got his little paper party blower, right? So he's super happy. Now, we're going to move on. This is 1s2, 2s2, 2p6 is the electron configuration for neon. Now we're going to move on. We're going to do an element that's a lot larger because you're not going to fill these one at a time. I'm just going to give you an element on the table, and it might be element 77, and you have to figure out how to fill that. So we're going to talk about how you're going to use the periodic table to fill an orbital diagram and write an electron configuration. Basically, though, you're going to, for an orbital diagram, you're just going to look at how many electrons something has. Nickel has 28 electrons. And you're going to fill in arrows until you get to 28. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, this 4s is lower in energy than the 3d. And we're going to talk about how you're going to remember that soon. But so far we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28. Remember that those electrons will be half filled until they have to pair. The electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Those superscripts should all add up to 28 electrons, and there should be 28 arrows on our orbital diagram. Now, one other thing I want to tell you is that this is what one orbital diagram looks like. Sometimes, though, to save space, we don't draw them like this. We draw them horizontally in a line with boxes or with lines. So these are all kind of the same thing. Now, if we want to use the periodic table to write an electron configuration, let's talk about that. So the periodic table can be divided up into these different blocks, right? So the S block is the first 2 columns. The P block is the far right 6 columns. So the representative elements comprise the S and the P blocks. The transition metal block is the D block, and the lanthanides and actinides at the bottom is the F block. So those are shown with different colors that you can see there. The row represents the shell. Right, so if N is 1, that's the top row, the first shell. And you can see that there, 1s, 2s, 3s, 4s, right? Now, one of the things that you should note is that the fourth row starts with 4s, and then it becomes 3d. So remember, the 3d orbitals are actually higher in energy than the 4s. And I'm not sure how you're going to remember that. There is a little trick I can show you if you want to see it on how you remember that, or you can just remember that the number goes down when you get to 4. When you get to the D block, the number goes down. And then when you get to the P block, it goes back up to 4 again. So 4s, 3d, 4p. And that's true all the way across. Okay, so let's then we'll write the electron configuration for germanium. Germanium is here on the periodic table. So when we think about the different blocks, that's here. Okay, so germanium is in that spot that's shown in yellow. So we're gonna use the periodic table to write that electron configuration. So here is our problem, and what we're gonna do is start with the spots on the table. So we have 1s, 1, 1s2. So those are the first 2 electrons, 1s2. And then we have 2s. There's 1, 2 electrons, 2 boxes there, which means 2 electrons, 2s2. And then in the 2p section, we have 1, 2, 3, 4, 5, 6 boxes, which means 2p6. The 3s, we have 3s, and there's 2 boxes, which means there's 2 electrons, 3s2. We move on to the 3p, and we circle 1, 2, 3, 4, 5, 6, which means we have 3p6. So each box represents an electron, right? So we have 4s, 2 boxes, which means 4s2 electrons. And then now we move to the 3D section, and we have 10 boxes here, so 3D 10. And now we have 4p, and we're going to stop when we get to germanium. So 4p2, right? And so that is our final electron configuration. So you'll see each box is like an electron, okay? So you're going to find that element on the table. You're going to think about the periodic table with this, S block, P block format. You'll have to remember that when you get to the 4th row, that when you get to the D block, that it goes down a number. When you get to the F block, it also goes down a number. So if you remember, the lanthanides follow lanthanum on the periodic table. And so that is 6s. So once you fill the 6s electrons, then you move to the 4f, and then to the 5d, and then back to the 6p. So we'll do another practice with that.